Okay, so before you actually open your Chapter 5 notes, let's make some predictions. So I have this graph here that's showing the amount of time it takes for a car to accelerate from 0 to 60. That's the response variable. And then we have weight on the x-axis, how heavy the car is, and then horsepower is the color. So you can see it's putting it into 5 different categories of horsepower based on the color. Okay, so here's the predictions I want you to make. First of all, think about a simple regression model. So if we were to fit this model with only weight as the predictor, what would the slope look like? Okay, then think about a multiple regression model. So here we have both weight and horsepower as predictors. What do you think the slope for weight would look like in that model? And I'll give you a little bit of a hint that you need to think about how the interpretation changes. Okay, so pause the video here and think about in each model, is the slope going to be positive, negative, or close to 0? Okay, so actually just by looking at this, I can tell that in a simple regression model that the slope for weight is going to be negative. Basically, I'm just going to ignore the color altogether, not pay attention to the color, and just look at the dots themselves. So if I were to do that and try to draw a regression line, maybe it would look something like that, right? Definitely a negative line. Whereas if we look at the multiple regression model, we want to say, what's the relationship between weight and acceleration controlling for horsepower, right? So in each of those horsepower groups, low to high, in each of those groups, there's a positive relationship between weight and acceleration. All right, so we can look at things a little more detail here now that we have the output. Let's start by interpreting the slope for weight. So this is just a simple regression model. So we're going to say as weight increases by 1 unit, so we have to see what the units are. Of course, I didn't write this down. I'm pretty sure it's pounds. As weight increases by 1 pound, the predicted acceleration decreases. And that's because we have a negative slope, right? Predicted acceleration decreases by this amount, 0.0014. And remember, if your acceleration time decreases, that means that you have faster acceleration. Okay, so we already saw in the other graph why we have a negative slope here. So it would be kind of surprising that heavier cars are accelerating faster, but we already saw that that's related to the horsepower. But there's still something that's a little bit strange here, because this is a really small slope, and yet we also have a really small p-value, right? That seems strange. How could a slope that seems pretty close to 0 give us a small p-value? So go ahead, pause the video one more time, and there's actually 2 things that are related to this. So see if you can come up with 2 reasons why you might have a small slope close to 0, and a small p-value, statistically significant evidence. All right, so this seems like a contradiction, that we would have a slope that's really close to 0, and yet we have strong evidence that the slope is not equal to 0. So there's 2 reasons for this. One is that, remember, when you're talking about slope, units matter, which I know I was a terrible example because I didn't put the units there in pounds. But if you think about the units here, an increase of 1 pound in the context of a car is a very small increase. So we don't expect that to change very much, right? Also, acceleration, we don't have a huge range of acceleration times. So those units matter too. The other thing is that this has 392 cars. So we do have a large sample size here. And remember, with a large sample size, you can end up with strong evidence even if your effect is pretty small. Okay, so let's get to the multiple regression model now. So in multiple regression, remember, a slope describes the effect of an explanatory variable after adjusting for the effects of other explanatory variables in the model. So you can sort of even see this in the graph, right? We're breaking it down by horsepower. So essentially, we're holding horsepower constant, right? We're looking at the high horsepower cars all together, So we've got like this orangey color, those are the high horsepower cars, and we can look what's going on within that group, and we can look within the low horsepower cars. So we're sort of holding horsepower constant there. So when we do that, when we look at the effect of weight controlling for horsepower, notice that the sign has changed, right? This slope has changed from negative to positive. This is going back all the way to like the first week of school. If it changes from negative to positive after adjusting for another variable, remember that's called Simpson's paradox. All right, so we interpreted the slope for simple regression. Let's do it now for multiple regression. And it's going to start off the same way. So we're going to start off by saying as weight increases by 1 pound, predicted acceleration now increases. So we're talking about slower acceleration times here. As weight increases by 1 pound, predicted acceleration increases by 0.0023. So far it looks the same, but we're going to add this tag, holding horsepower constant. So we've already talked about what it means to hold horsepower constant in the graph, but let's think about what it means in terms of the actual prediction equations. Basically, the idea is that you would pick a certain horsepower and just fix it there. So let's say that we're going to fix horsepower at 50. So basically we're saying at this moment, we're only going to look at cars that have a horsepower of 50. And remember, that's our x2. I'm going to write that down. x2, which is horsepower, is 50. Okay, so I'm going to plug into the prediction equation and I'm going to plug in 50. So I've got y hat is 18.44 plus 0.0023 x1 minus 0.0933, and here's my x2. I'm going to plug in 50. So notice now this is just constants, so I can put that together with the intercept, and I end up with 13.775 plus 0.0023 times x1. Remember, x1 here is weight. Okay, so you could plug in for a particular value of horsepower and get the equation that relates weight to acceleration. So now let's do the same thing, but let's change it to a different horsepower level. So now I'm going to look at only the cars with 100 horsepower. So I'm doing the same thing, except when I get to x2, I'm going to plug in 100. And again, this is a constant, and so it's going to be part of my intercept, and I get 9.11 plus 0.0023 times x1. Okay, so let's kind of draw this on the graph, mimicking what we've got up there, but this one is just looking at this model. So we have acceleration here, and weight on our x-axis. So let's sort of draw the line. So if we were to draw the line for x2 equals 50, horsepower equals 50, maybe it looks like that. And then the one for x2 equals 100 is parallel because it's got the same slope, but it's lower. Okay, so then this is sort of the relationship. And remember, horsepower is also related to weight. The ones that are lower horsepower tend to be lower weight, so they're further over here on the left in the graph. And then the ones that are higher horsepower tend to be higher weight. They're a little further here on the graph. If you were to draw a line between them ignoring horsepower, so this line we're ignoring horsepower, you end up with this negative line. So that's how you have the different slopes. So one thing to point out about our drawing here is that we have these parallel lines. The reason that it's parallel is because there's no interaction term in this model, right? We have a term for the weight and a term for the horsepower, and they're separate. So what that means is that this model actually assumes that we have the same linear relationship, between weight and acceleration. So that's what we're looking at with the slope, the relationship between weight and acceleration. So this model assumes we have the same linear relationship between weight and acceleration for all levels of horsepower. So in other words, whatever we plug in for horsepower, we're going to get that same slope. So the key word here is that this model assumes that, right? It's not based on the data, it's based on the way we've defined our model. And actually, if we look at the graph, this may not be a perfect assumption, right? It seems like maybe the slope is changing a little bit, that these high horsepower cars have a little bit flatter slope than the low horsepower cars do. So that's an assumption that we're making.